Hello everyone, my name is Juney Lee and I'm a postdoctoral researcher at the Block Research Group of ETH Zurich in Switzerland. Welcome to this Introduction to Library Academy advanced class on funicular shell design explorations using RhinoVAULT 2. RhinoVAULT 2 is a Rhino plugin for form finding of compression-only shell structures developed based on Compass framework. Compass is an open source Python-based framework for computational research and collaboration in architecture, engineering, and digital fabrication. The Block Research Group at the Institute of Technology and Architecture at ETH Zurich is led by Professor Dr. Philip Block and Dr. Tom Van Melle. Research at the Block Research Group focuses on several core areas, including analysis of masonry structures, graphical analysis and design methods, computational form finding and structural design, discrete element assemblies, and fabrication and construction technologies. The central goals of our geometry-based approach are to understand the real demands of complex structural design and engineering problems, and to develop new algorithms and efficient, accessible tools for structurally informed design. First, I would like to begin this introduction video for RhinoVAULT 2 by presenting some of the core theoretical principles and background information on the thrust network analysis, which is a graphic statics-based form-finding method that RhinoVAULT 2 is based on. Graphic statics is a design and analysis method for two-dimensional discrete structures that relies on geometrical rather than analytical or numerical representations of the relation between a structure's geometry and the equilibrium of its internal forces. Graphical representation of equilibrium using reciprocal form and force diagrams provides invaluable insight for designers and improves intuitive understanding of a structure's behavior through a visual medium that is easier to digest and more transparent than conventional arithmetic or numerical methods. The magnitude of the internal force in a member of a structure in static equilibrium is the length of the corresponding edge in the force diagram, which are parallel to one another. During the 19th century, graphic statics enabled engineers to design and analyze complex truss structures by simply drawing the equilibrium of internal force vectors instead of long and tedious hand calculations. Graphic statics was used by notable structural engineers at the time to build large bridges and monuments. Because graphic statics is a method for analyzing structures with only axial internal forces, it was the perfect method for designing and analyzing these large steel truss structures. At the turn of the 20th century, the building industry witnessed a growth in reinforced concrete construction. Graphic statics, which is appropriate for structures with linear members carrying axial forces only, was no longer adequate for analyzing structures made of solid and indeterminate materials like concrete. As a result, the methods of designing and analyzing structures gradually became more dependent on numerical methods based on linear algebra. Additionally, the increasing computational power of computers gave birth to finite element modeling and analysis, which was much faster and efficient than manually drafting form and force diagrams by hand on paper. However, there has been a recent revival of graphic statics through computational implementations, which have enabled dynamic interaction between form and force diagrams with real-time visual feedback. These interactive implementations of graphic statics allow users to directly control the geometry forces, which enable force-driven design approaches with high formal freedom to explore structurally informed geometries during early stages of design. Furthermore, the intuitive and visual benefits of graphic statics can be combined with more sophisticated form-finding algorithms to explore structures beyond the 2D plane. Graphic statics combined with computational form-finding is a fundamental theory and principle behind thrust network analysis, TNA. TNA is a methodology for generating compression-only vaulted surfaces and networks. The method finds possible funicular solutions under gravitational loading within a defined envelope. Using projective geometry, duality theory, and linear optimization, it provides a graphical and intuitive method adopting the same advantages of techniques such as graphic statics, but offering a viable extension to fully three-dimensional problems. In TNA, the horizontal projection of the vaulting shell structure is used as a form diagram. Force diagram of this projected form diagram represents the horizontal equilibrium of the shell structure. The thrust network, or the thrust diagram, is a network that represents the shell structure, which is discretized into line segments. In contrast to other form-finding methods based on black box numerical calculations, TNA offers the force diagram, which is not just a visualization of horizontal equilibrium of the shell structure, but also the means through which the designer can explicitly modify the internal forces, thereby enabling a careful and controlled transformation of the geometry of the shell structure, while the designer is constantly being informed of the internal force distribution. The ability to control the form-finding process through precise and controlled modification of the geometry of forces is the key benefit that is exclusive to TNA. RhinoVAULT is the implementation of the theory, method, and form-finding procedures based on TNA. First developed in the early 2010s, RhinoVAULT emerged from current research on structural form finding using the thrust network approach to intuitively create and explore compression-only structures. RhinoVAULT makes it easy to explore complex shell geometries in an intuitive manner while constantly informing the designer of the relationship between form and forces. Although it may be difficult to learn at first for new users, all the functions and solving algorithms of RhinoVAULT are designed to be clear and explicit in its purpose and procedure, such that the user is not only naturally educated on both the tool itself and the process behind it, but also gains structural insight thanks to the force diagram. The structural insights gained by constantly being aware of the symbiotic relationship between the form, force, and the thrust diagram is a very important message of RhinoVAULT. While sophisticated computational tools should give the user more freedom and control over the form, it is also important in the current digital design age for tools to also educate the user such that more structurally informed design decisions and modifications be made. By allowing users to shape structures by designing and modifying the geometry of the force diagram, RhinoVAULT significantly expands the design space of compression-only shell structures. The development of RhinoVAULT 1 has stopped. RhinoVAULT 2, or RV2, is a Rhino plugin that replaces RhinoVAULT for Rhino version 6 and above. Unlike RhinoVAULT, RV2 no longer relies on Rhino for its computational implementation. Instead, it is built entirely with open source packages from the Compass framework and its ecosystem, and will therefore be available not only for Rhino and Grasshopper, but also for Blender and other tools with a Python scripting interface, and ultimately even in the browser. RhinoVAULT 2 is an open source research and development platform for funicular form finding built with the Compass framework, a Python-based framework for computational research and collaboration in architecture, engineering, and digital fabrication. The Compass framework is created with three main objectives. First, don't repeat yourself or others. Compass provides a base framework and easy access to peer-reviewed computational research, libraries, and tools, such that you don't have to reinvent the wheel over and over again. Second, sharing your work. Compass is an open source framework with a permissive license. Research that is based on Compass or that is compatible with it can be easily shared and reused across platforms and software ecosystems. And lastly, collaboration. Architecture, engineering, fabrication, and construction research and development is highly multidisciplinary. Compass simplifies collaboration between individuals and teams with various academic backgrounds. Please visit the online documentation of the Compass framework for more information. The main library of Compass framework provides flexible data structures, a geometry processing library, robot fundamentals, numerical solvers, and various other components as a base framework for computational research in architecture, engineering, and construction industry. The core library of Compass can be used to develop extensions and add-on packages which are developed by different users with their own research projects and computational work. Compass TNA is an extension package that is a computational implementation of the thrust network analysis. RV2, in essence, is a user interface, and its primary purpose is to enable a user-friendly implementation of TNA-based functionalities and algorithms within the CAD environment of Rhino. In this section, I would like to present the workflow of RV2 by going through the user interface in a sequential manner from left to right that follows the form-finding procedures of TNA. The first step is to come up with the concept or an idea for the pattern, which represents the horizontal projection of the eventual shell structure. The make pattern function creates a pattern object from various inputs such as lines, Rhino surfaces, Rhino meshes, boundary curves, and so on. A pattern object is a network of segmented lines. Once a pattern object has been generated, boundary conditions need to be defined. Define boundary conditions function allows users to define the anchors of the structures, which are displayed in red here. Anchors are fixed vertices or support points of the structure where external reaction forces will be present. Once the boundary conditions have been defined, the pattern object can be turned into the form diagram. Once the form diagram has been created, the dual diagram can be created. The dual diagram represents the topology of the force diagram, but its geometry is not yet correct and does not represent the horizontal equilibrium of the form diagram. For this example vertex of the form diagram, we see here that the corresponding edges in the two diagrams are not yet perpendicular. In RV2, the corresponding edges in the form and force diagrams are perpendicular, which is a different convention than the parallel orientation used by RhinoVAULT 1. The horizontal equilibrium solver iteratively updates the geometry of the dual diagram such that the corresponding edges now become perpendicular to one another. Once the horizontal equilibrium has been found, we observe here that the corresponding edges are now perpendicular to each other. The last step of the form finding process is to solve the vertical equilibrium of the structure. Vertical equilibrium uses the geometry of the form diagram to compute the coordinates of the vertices of the thrust diagram in the z-axis. Given a target height, the vertical equilibrium iteratively computes the new coordinates of the thrust diagram such that the eventual geometry of the thrust diagram is in equilibrium with itself weight. Once the geometry of the thrust diagram has been found using the target height, the three diagrams can be modified to do further iterative explorations. These features will be presented more in detail during the class. Utility functions and various setting options will also be addressed more in detail during the class. In the final section of this introductory video, I would like to show you how you can install RV2. The UI of RV2 is only compatible with Rhino for Windows. Although RV2 can be installed for Rhino Mac, the toolbar or the menu will not be available. In this class, we'll be using RV2 with Rhino for Windows only. As the first preparation step, open Rhino and run the command edit Python script once, then exit Rhino. This will initialize some internal Rhino folder structure, which is necessary for the installation of RV2. Then go to the GitHub repository of RV2, then navigate to the release section on the right side of the page. Then download the latest stable version of RV2. Although these releases work perfectly fine, a newer version with the latest features and developments will be released exclusively for this class in the beginning of December. Navigate to the folder where the RV2 installation file is downloaded and run the installation file. If you see the following prompt, click on More Info, then choose Run Anyway, and click Yes to allow RV2 to make changes to your computer. After the installation interface shows up, click on the Install RV2 button, then choose a location to install RV2 on your computer. It is important to note here that the path to the installation folder cannot contain any spaces or special characters. Also, please do not use your program files folder for the installation, since this requires special admin privileges. The installation usually takes 1 to 2 minutes. After the progress bar finishes, click Yes twice in User Account Control. The installation is successful if you see this following window. Press any key to close the window. Next step is to activate the RV2 toolbar in Rhino. In the main drop-down menu of Rhino, go to Tools, then Toolbar Layout. In the pop-up window, click File, then Open. Navigate to the location where your RV2 is installed, then go into the folder called Dev, where you will find the file rv2.rui, then open it. Under the Toolbar section, you should now see RV2. Tick the checkbox. The RV2 menu and toolbar will now both appear in the Rhino user interface. Finally, to check that everything has worked, click the Initialize RV2 menu item or the toolbar button. You'll be asked to read and accept the terms and conditions and user agreement, after which the welcome screen should disappear. If Rhino says command not found, please run the command edit Python script to open the script editor, then restart Rhino. Then try the initialization again. Finally, I would like to tell you more about additional resources for RV2. If you have any issues with the installation, questions about the tool, or suggestions, please navigate to the Issues section on the main GitHub repository page of RV2. Then click on New Issues on the right side of the page and file your issue there. One of our developers will assist you as soon as possible. All of the instruction details, theoretical background, explanation of the functionalities and algorithm, tutorials, and examples can be found in the online documentation of RV2. Please visit the RV2 online manual and documentation for more information. This concludes the introductory video for the Live Academy advanced class on funicular shell design explorations using RhinoVAULT 2. Thank you all for listening, and I'm very much looking forward to exploring the world of funicular shell structures with you on Tuesday, December 8th.